So this time we want to look at example 5, which is not nearly as complicated and long as example 4, which is really quite difficult. Now we want to look at example 5, and we can write it in the more fractional form that we're accustomed to. F of x is equal to the natural log of x divided by x squared. So this time we have a mixture of different types of functions. We have natural log and a polynomial x squared, and they're in ratio to each other. So we want to start with the domain, which of course is all the things that it cannot be. We have two considerations. We have the denominator cannot be 0, so we're going to have to toss out 0. But we also have that the natural log's argument, which is x, has to be strictly positive. So we have two conditions we have to think about here for the domain. So when we're looking at the domain, the first thing that we note is that x squared cannot equal 0, so x cannot be 0. For the natural log of x, we know that x has to be strictly greater than 0, which means that our domain is going to be from 0 to infinity. So any value larger than 0, so 1/2 works, negative 1/1,000,000th, or 1/1,000,000th works, not negative, positive, strictly positive. So this is what we're starting with. So when we're looking at this, anything that occurs to the left of 0, we're going to ignore, and anything that brings up 0, we're going to ignore because they're not in the domain. Now we want to look for symmetry, but the problem is we can't really replace x with negative x in the numerator. It doesn't give us the same function, all right? We don't have even odd behavior. So when we look at that, we can replace the symmetry by replacing x with negative x. And of course, the natural log of negative x is defined. It just means that the x values would have to be negative so that the argument is again positive. And then when we replace the denominator with negative x, we get the same thing again. So we have negative inside the argument to the natural log, and the denominator is the same. But that negative can't come out of the natural log. It can't pull out. So this is not the original function, clearly, because this is a negative x in the argument. But it's not the opposite of the original function, which would have the negative on the outside of the function. So it's not symmetric. So no symmetry. Right? Now, the next thing that we want to look at are the intercepts, the x and y intercepts. But again, our domain is from 0 to infinity. So x can't be 0. And if x can't be 0, we don't have a y-intercept. So when we're looking at intercepts, it's only going to be the x-intercept that's a possibility. Y-intercept, that's when x equals 0, but it's not in the domain. So we have no y-intercept. Now, when do we get the natural log of x equal to 0? That would be for the y value equals 0, which is the x-intercepts, when the y is equal to 0. And the natural log of x is 0 when x is 1. So when x is 1, we have the natural log of 1 equals 0. So this would be the ordered pair 1, 0. So we know it crosses the x-axis at 1, 0. Now, what is the next information that we want to look at? End behavior. So we want to look at what happens at the ends of the graph. Now, in our case, that end behavior is going to be as we approach the right side, since on the left side, it's got to be approaching 0 from the right. So when we're looking at this particular behavior, we want to look at what happens as x goes to infinity. So we have the limit as x goes to infinity, and this is our end behavior. We have the limit as x goes to infinity of the natural log of x divided by x squared. Now, x squared is a polynomial which grows an order of magnitude much larger than natural log of x. So we have what are called magnitude of going to infinity. That doesn't sound right. Surely I can put it better than that. An order of magnitude larger as it approaches infinity. It grows faster, in other words, the polynomial does. And so because it grows so much faster than natural log of x, it overpowers it and drives the whole thing towards 0. And we discussed this when we did the 4.6 part 1. So if you're looking for that information, look at the video on 4.6 part 1. So this approaches 0, all right, as x goes out to infinity, right? So we have this weird behavior out here. Now we need to look for vertical asymptotes. And we do have a vertical asymptote. That would be the next thing that we're looking for. Our vertical asymptote is what the denominator can't be that does not cancel and disappear. So our denominator is x squared, so x cannot equal 0. So we do have that information so far. So let's put what we know so far, which is just the ordered pair 1, 0, and the vertical asymptote x equals 0. So we have an ordered pair at 1, 0, and we have an asymptote at x equals 0, right? So we're going to make the asymptote blue again, and we're going to make it dashed. So it goes like this, and we'll make our ordered pairs show up darker as black, makes it show up better, and we'll label it. So that's the only information that we have so far analytically. Now we want to look at holes. Are there any holes? Well, no, there are no holes. X squared doesn't cancel with the natural log of x. The natural log of x is a unit, right? It all goes or none of it goes. And I don't have a natural log of x down here. And I don't have an x by itself as a factor in the numerator. So I have no holes, right? Now, the next thing that we wanted to look at is, of course, the behavior due to calculus. So this is going to be the first derivative test, which gives us increasing, decreasing, and relative extrema. And then the second derivative, which gives us concavity and inflection points. So we'll start with the first derivative, and we're going to find increasing, decreasing behavior. So we need to find the first derivative. So we're looking at a function of natural log of x divided by x squared. So if we want to, we can write our function over here in a couple of different ways. You can leave it as natural log of x over x squared, or you can write it as x to the -2 natural log of x. Now notice I chose to put the x to the -2 at the front, because otherwise it has a tendency to creep inside of the argument to natural log, and it's not a part of that. So you can use whichever method you like. This time I think it might actually be a little bit easier. Well, I don't know. Quotient rule is still my favorite, but I think it'd be just as easy with the product rule. So choose your method and go ahead and find the derivative. So I'm going to do the first. The derivative of natural log is 1 over x. The derivative of x is 1 times the bottom, which is x squared, minus derivative of the denominator, which is 2x, times the numerator, which is natural log of x, all divided by the denominator squared. So we have a square squared, which is going to give us the 4th power. Now the x squared divided by x gives me x minus 2x natural log of x divided by x to the 4th. Now I can factor something out of this. I can take an x out of the numerator, and that would give me x times 1 minus 2 natural log of x. That x cannot move. It's part of the argument of the natural log over x to the 4th, which cancels one of the x's in the denominator. So I end up with 1 minus 2 natural log of x divided by x cubed. So that's my derivative. Now I have 2 types. The 2 types are type 1 and type 2. So I'm looking for critical values of the first derivative, or critical points. So type 1, I have the first derivative equal to 0, but the function exists. And type 2, I have the first derivative does not exist, but the function does, but it's in the domain of the function f of x. Now remember, our domain is from 0 to infinity, open 0. So we'll make note of the domain again up here. So the domain omits 0. So even though clearly it's not defined when it's 0, that's not in the domain. So it's not a critical value. To be a critical value, you have to be in the domain. So we have none of type 2, which is not a shock. They're pretty rare. They only typically come up when we have radicals or roots in the numerator. And then when we take the derivative, we get a radical or root in the denominator, which was not there originally. That will create definitely a type 2. So now we're looking at type 1s, which is the numerator equal to 0. So we have 1 minus 2, natural log of x equals 0, which means 1 equals 2, natural log of x, or natural log of x equals 1/2. Now we want to switch this into exponential form. So this is more of your college algebra coming back again, or pre-calculus if you took that in high school. Hopefully you did. But if not, we have the base e, the power is 1/2, and it equals x, the answer part. So e to the 1/2 power equals x. So that's our critical value. So we do have a critical value. It's just not a particularly lovely one. And e to the 1/2, of course, can also be considered to be the square root of e. So you can think of it either way. Now, if you want to do that, then you need to find that power so you have an approximation for it. My calculator went to sleep. So I have e to the 0.5 power, or the 1/2 power, which gives me about 1.65 roughly. I need to be able to break up the number line. So again, I'm going to start with the domain of the function, and the domain of the function is going from 0 to infinity. So from 0 out to infinity. So mine is going to be broken up by the square root of e, or e to the 1/2, and I need test points. So 1 looks like a good test point, except, well, no, yeah, 1 looks like a good test point, and 2 looks like a good test point. And again, we're just looking for the sign of the derivative, not the actual value. So we're looking for the sign of f prime. Now, notice that because our domain only goes from 0 to infinity, that x cubed is always strictly positive. So even though cubes normally take the sign of whatever it is, ours are only positive. So x cubed is positive. So we only have to look at the numerator. So 1 minus 2 natural log of x. So that's what we need to consider. And at our first test point, which was 1, the natural log of x is 0. So I get 1, which is positive. And at 2, this I may have to do a little bit more work on. At 2, I'm going to have actually the value of 1 minus 2 natural log of 2. So I might need my calculator to figure out if that's positive or negative. And when I look at that, I've got 1 minus 2 natural log of 2. And it turns out to be a negative value. I don't care about the actual value. It's actually 0.386, but I care about the sign. So this one is negative. So when I'm looking at this one, then what I see here is that I've got a decreasing behavior and an increasing behavior. And I've got decreasing from the square root of e to infinity. And I've got increasing from 0, which is where the domain starts, up to the square root of e. And I've got a positive uphill here and a downhill here, which means that I have a relative maximum, or possibly an absolute maximum, hard to say. So I have a relative max at the square root of e. Now I need to find the function value, and remember my function is natural log of x over x squared, all right? So that was my original function, this natural log of x over x squared. So to plug in the values, I've got f of x equal natural log of x over x squared. So plugging in my square root of e, I have the function value at square root of e, which is equal to, sorry, I got a tickle in my throat. That's going to be the natural log of the square root of e, or e to the 1/2 power, over the square root of e squared. Now, I can also think of this as e to the 1/2 power, which is better in this case, because the natural log of e to a power, the natural log and e to a power, they're inverse operations. They undo each other. So I get 1/2 from the numerator and e in the denominator. So I have 1/2 divided by e, which is equal to 1 over 2e. So my relative maximum is at 1 over 2e. Now, we're going to come over here, and I'm not real sure how we're going to enter e, but we'll try just e and see if that works. So we have the square root of e, 1 over 2e. So let's try to enter that as a value. So we have the square root of e. Yep, that's the value, comma, 1 divided by 2e. Right. Close that up. So we have an ordered pair, and we're going to label it, and we're going to turn it black. So this is a relative maximum right there on our graph. All right. Okay. And we can actually change the label. If you want the label to be exact, you can type it in square root e, comma, 1 divided by parentheses 2e. Oops, yes, that's right. Make sure that you use parentheses around the 2e so that the whole thing is in the denominator. And we'll put parentheses at the front. Oops, wrong way. There we go. So that's square root of e, 1 over 2e is that actual point. Now we want to take a look at the concavity and inflection points. So we need the second derivative. So coming back up here, we need to find our first derivative, which is this 1 over 1 minus 2 natural log of x over x cubed. Now we want to find the second derivative. So we want to look at concavity and inflection points. So we need the second derivative. So I'm going to take the second derivative of that. So I have the derivative of the numerator. Derivative of 1 is 0. So derivative of natural log is 1 over x times 1 times the negative 2. So I get negative 2 over x times the denominator, x cubed. So that's derivative of the numerator times the denominator minus derivative of the denominator, which is 3x squared, times the numerator, which is 1 minus 2 natural log of x, all divided by the denominator squared. So we have a cube squared, which is going to give us the 6th power. Now we're going to go ahead and do some algebra on this to reduce it. So x cubed divided by x gives us a negative 2x squared. Distributing out the next term, remember it helps to actually draw the arrows so you don't mess up the signs. And that gives us negative 3x squared, and then plus 6x squared natural log of x. So check your signs again and make sure it looks right. So this times this gives us negative 3x squared. Negative 3x squared times negative 2 is positive 6x squared with the natural log of x factor on the back. And then it's all going to be divided by x to the 6th. One base, 2 powers, you multiply the powers. That's the rule from algebra. So that gives us x to the 6th. Now notice that the numerator, all 3 terms, have a common factor of x squared. And the negative 2x squared minus 3x squared, I can actually combine. So I'm going to do a little bit of combination here. I'm going to create some space, and I'm going to combine these two terms into negative 5x squared. Then I can take out the x squared, and that will give me x squared times negative 5 plus 6 natural log of x, all divided by x to the 6th. Then I can cancel the x squareds. So finally, for the second derivative, I have, I'm going to leave it in this order because I don't want anything to creep up inside the argument to natural log of x. And this will give me x to the 4th. 2 on top, 6 on bottom, cancels 2 on the bottom, and we're left with 4. Okay, now what do we have to do? What were we doing again? Oh yeah, we're trying to find the concavity and inflection points. So we need the critical values of the second derivative. So we're looking for critical values of the second derivative or critical points. We have type 1, which is the second derivative equal, hang on a second. I may have to shut down and open up again. So we have second derivative equal to 0. Looks like it's changed colors on me. And we have type 2, which is second derivative does not exist, but the first derivative and the function do. But in the domain of f and f prime. And this time, however, we see that the only value that causes the second derivative to be undefined is again 0. So, but that's not in our domain. So we have no type 2s. We have none of these. And then type 1 would be the numerator equal to 0. So we can set the numerator equal to 0 and switch to exponential form as we did before. So this is going to be negative 5 plus 6 natural log of x equal to 0, or 6 natural log of x equal to 5, or natural log of x equal to 5 over 6. Switching to exponential form, e to the 5 over 6 equals x. So we have e to the 5/6 as a possible inflection point. So now what we want to do is we want to draw our number line. Remember that we're starting with a domain of 0, and we have e to the 5/6, which is our only possible inflection point. So we want to include on our number lines anything that's omitted from the domain or is a critical value for that particular derivative. So now we have the sign of the second derivative. And I need to know what e to the 5/6 is approximately. So using my calculator, I have e to the 5 divided by 6, which is about 2.3. So I'm going to again use the test point of 1 and a test point of 3. So the sign of the second derivative, I'm going to look at the second derivative, which is this particular value right here. Negative 5 plus 6 natural log of x over x to the 4th. So looking at this, the x to the 4th will be positive no matter what. And in this case, our domain is always positive, so it's doubly always positive. So that's not a problem. Looking at 1, the natural log of 1 is 0, which is why it's a good test point. So the 6 natural log of x drops out, and I get negative 5 over a positive, which is negative. So that tells me it's going to be concave down over the interval from 0 to e to the 5/6. Okay. And then I'm looking to see if it's concave up. I don't know. That could be a cusp, and it might not change concavity. So it's only a possibility. So then I need to use my second test point, which is the third power, or the 3 rather, not third power. So finding f double prime at 3, this gives me negative 5 plus 6 natural log of 3 over 3 to the 4th, which is of course positive. So then I want to take my calculator and figure out what the sign of the numerator is. So I have -5 plus 6. Oops. Somehow clear. Somehow I put in times instead. So -5 plus 6 natural log of 3, which ends up being positive. So this is going to be a positive value. All right, which tells us it's concave up from e to the 5/6 power to infinity, that part of the domain. That means we do have a change in concavity at e to the 5/6. So now we need our original function again to find the inflection point. So we have an inflection point at e to the 5/6. And remember, our function, of course, back to the original, was the natural log of x over x squared. This leads to the value you see above. Okay, let's now find the value where where the inflection point is. So you can see that it's at x. Oops, I've got the wrong thing written in there. I've got e to the 5/6, so I replace that in the original function. Then I have natural log of e to the 5/6 over e to the 5/6 squared. That's my function, my original. And then when I'm looking at it, natural log and e to the 5/6 are inverse operations. So that just gives me 5/6. And when you have a base to 2 powers, you multiply the powers. So 5/6 times 2 gives me 10/6, which reduces to 5/3. So the 6 drops down and I get 5 over 6e to the 5/3. So 5 divided by 6e to the 5/3 power. And when we're looking at our graph over here, we can see that we do have this here. Notice that it is approaching, if we scroll out, we can see that it is approaching the vertical asymptote of x equals 0. And when we scroll in, we can see that it is concave down, looks like all the way out here to the inflection point at e to the 5/6 power. So we have concave down out on that, and then concave up from e to the 5/6 to infinity. It's more difficult to see that because it's so subtle, but it does start bending up, and that makes it concave up. And then we can look at the increasing and decreasing behavior, which came from the first derivative. So scrolling up, we know it's increasing from 0 to the square root of e, which it is, and the square root of e is where we find that relative maximum. And then it's decreasing from the square root of e to infinity. Notice it does have the end behavior that we predicted. It approaches the x-axis, y equal to 0. And we do have a relative maximum right here. So we've got all the information put together in one place. And hopefully this helps you to understand how to use algebra and calculus to predict the exact shape of a graph.